Got it. Being nice. We have relatives in Georgia and Texas and Oklahoma. And the Oklahoma, my brother-in-law in Oklahoma is right smack in the middle of the tornado target.
Yeah.
It's just remarkable how they just pass around him. And there's a niece in Louisiana too, not far over the border from Texas. And what's the name of it? Oh, I forget the town in
Like Lake Charles or
Texas. I'm not sure. It's I can't recall my other brother-in-law. They're all over Florida, Georgia. So we've been down a few times, but we always go down in the nice weather. So
Yeah.
when we were in Texas, of course, it was great. And we say, wow, this is a good place to live. And then the folks that live there say, no, it gets to 110.
Yeah.
So much for that.
I took my son to Las Vegas in the spring and he's like, we should move here. The weather's great. I'm like, it's great now.
That's right. Yeah. So it's strange. We haven't had no snow in New Jersey this year.
Oh, wow.
That's remarkable. So things are changing. So we'll see where that goes.
Yeah.
Does your work take you out different places?
I used to travel quite a bit, maybe, not quite a bit, but I would travel maybe four or five times a year. I'd go somewhere to give a seminar at a university or something like that. But then after COVID, people just started doing stuff online. So, the online is very convenient and that's nice for everyone, but
just to interrupt.
Yeah.
Sorry.
Yeah.
I wound up kicking the live stream off a little early. So just to let you know, in case anything that you're discussing, if you don't want to go out, we'll cut out the beginning part when after it's been recorded. So I just want to let you. I'm just trying to get things set up here, and I kicked off a bit earlier than I expected it to. So
that's fine.
Okay. Just tell me when.
Don't want any state secrets to go out.
I don't have any state secrets.
No, it's John that we're worried about.
Me.
I think everybody's situated here, so we can actually kick off. If you want to introduce John, please.
Oh, shall I introduce right now?
Go ahead.
Okay. And then you'll be on. Tonight we welcome from the professor of physics, Rhett Allain, from Southeastern Louisiana University. He's the author of the Wired magazine science blog Physics. An interesting little tidbit is he was the science advisor for the Discovery Channel Mythbusters, both back at the original series and also today for the new Mythbusters. So technical consultant for the CBS show MacGyver. And so everyone, welcome Dr. Rhett Allain. Doctor.
Thank you very much. So I'm going to talk about things that I love because I like to talk to myself, and that's the best way for me. And I love science. I love physics, and I love science fiction. So there are a lot of different things we can talk about science fiction, but really I'm going to use a couple of examples to talk about physics and science. There's a link down here. You can see at the bottom bit.ly/sci-fi physics. That's a list of more stuff than you could possibly read. So when I write something new for Wired or for some other place, I'll post a link there, and then it keeps track of all my science fiction and Star Wars stuff. So if you want to see that, if you want to complain, there's my email, so you can email me if I said something wrong, which sometimes I do on purpose. But let's get started. You didn't think there'd be a quiz, but there is indeed a quiz in this thing. So here's a video. It's a video quiz. So we'll start with a video clip. This is Star Wars. I use quite a bit of Star Wars, and some people may say that's not science fiction. We could have that debate. It doesn't really matter. Star Wars is important to me. I like it a lot. So this is from episode 2, and we see R2-D2 flying And that's the scene that I want to look at. Now I have a multiple choice quiz for you. So what's wrong with this scene? What's wrong with the flying R2-D2? A, nothing. This is exactly what George Lucas wanted. He just wasn't able to do that in 1977 for the original Star Wars, because that's what the people say. Why R2-D2 flew in episode 2? Why didn't he fly in episode 4? Next. Well, why didn't he do this in the original trilogy then? That's a good question. Why didn't he? C, he wouldn't fly that way. And D, droids shouldn't fly. And that's not really an answer, but that's fine. And it's all a trick question, because I said you couldn't render R2-D2 with the Commodore 64, which didn't even come out until 1982, and it wouldn't do it anyway, but it's fun to think about that. So let's talk about this clip, because there's some really interesting physics in that clip. Imagine that two people saw this show, and their names are Aristotle and Newton. So Aristotle on the left did a lot of stuff about physics. He didn't really collect experimental evidence, but he came up with great ideas that people said, yeah, I agree with Aristotle. And still to this day, people agree with what Aristotle says. He says that if you exert a force on an object, if you have a constant force on an object, then it's going to move at a constant motion. And that seems to make sense. Newton, along with some others, Galileo in particular, said, well, no, actually, that's not quite true. A constant force on an object causes a constant change. So a constant force would make something change its motion. It would change its speed. It would speed up. So what does R2-D2 do in this case? Because he's got rockets. They're definitely pushing him forward. Does he even move at a constant speed? Well, we can analyze that by looking at the actual video clip. And this is something that I do a lot of. It's called video analysis of motion. The idea is to scale the video in some way, mark the location in each frame, and you can get position time data. And so this is position time data from the actual clip of R2-D2. And since it's position versus time and it's a straight line, that means he's moving at a constant speed. So yes, in the video, R2-D2 moves at a constant speed. Okay. But he's got his thrusters pushing him forward a little bit. So should he move at a constant speed, or should he not move at a constant speed? Well, he should be speeding up if the thrusters are pushing him forward. That's what Newton says. But we can fix it. Don't worry, we can fix this. So here is a diagram of R2-D2 flying. And I drew this because, you know, at the point I didn't want to use any Star Wars stuff, so I had to redraw my R2-D2. In Keynote, I did this in Keynote. So we really have three forces acting on R2-D2. There's the thrust, pushing in the direction of his legs, I guess you call those legs. There's the downward gravitational force. And then there could be a drag force. So the drag force is something that is in the opposite direction of motion because he's interacting with the air. So let's make some assumptions. Let's assume that this is Earth-like gravity. I mean, it's not Earth, and it's not even in our galaxy. It's a galaxy far, far away. But everyone looks like they're on Earth because they're on Earth. We know that. They're actually actors filmed on Earth. So why not? I'm going to say it's Earth-like gravity. So I know the gravitational field is just like Earth. I'm going to also assume that the air density is just like Earth, again, because it looks that way. If that's the case, I can model the drag force. One way to model the drag force is with this equation. It says that the drag force depends on the density of air, that's the rho, the size of the object, a drag coefficient that depends on the shape, and the velocity squared. So the faster you go, the more drag force you have. I already know how fast he's going. I just measured that. So with all this, I can get a drag force. And if I know the angle that his thrusters are, which I can also estimate, then I can calculate the gravitational force because I know how much is pushing him forward to counteract that drag force. And if I do that, I solve for his mass and I get 100 grams. So that's really, really, really low mass. The only way that this would work realistically is if he has such a low mass that thrust is barely pushing him up at all, and therefore barely pushing him forward to counteract that thing. And that's not realistic. And that's okay, right? That's okay. So I do want to show you a real jetpack, and this is the older style. We have newer jetpacks that are much cooler, but this is the 1960s jetpack. As he's flying around, you'll notice that when he's moving at a constant speed, his legs are hanging straight down, he's not pushing forward to move at a constant speed. And then when he goes to slow down and stop, his legs move forward because he has to have a thrust pushing him backwards. So it's kind of fun just to compare real jetpacks and droids, even though Star Wars isn't real. And that gets me to my most important point in this whole talk, because we're looking at things and we're saying, okay, R2-D2 flies wrong. Well, I could be this guy. The science isn't, that actually is me. So, the science isn't correct in this movie and it should be better. And there's a lot of people that say that. And they say, this shouldn't be wrong. It should be right physics. It shouldn't be wrong. But then you could get, on the other side, you could get someone like Arthur C. Clarke, and he could read my physics paper and say, there's no plot in this research paper and it needs to have better plot. And I actually kind of agree with him on that thing too. But and that's fine, right? Because we don't expect a movie to be physics. It's not about physics. And in fact, a movie has more than one, but let's say one primary goal. And this is what I like to say. The number one job of the movie is to tell a story. And if the science supports that story, that's great. And if it doesn't, then that's fine. It's a story. We don't have to have great science. And I just want to point this out because I don't want to be, that guy that's like, well, that's wrong. That's wrong. I love Star Wars and I love science fiction and I love physics. So I like to combine them together. And it's okay that they don't agree. That's okay. That's not the point. Now, there are some cases, I can think of a couple movies where there's just inconsistent and terrible science that does not further the plot. That's not good. But again, I still enjoy it. Okay, let's look at some other science examples from science fiction and Star Wars. And I'm going to start with this one. This is a space elevator. This is from the Apple TV series, the Foundation series, which of course is a book too, books. And I really enjoyed the show. But space elevators are really cool. And so what is a space elevator and what would happen if a space elevator breaks? That's what we want to talk about. So if you want to really understand a space elevator, you need to first understand orbital motion. And there's a bunch of pieces here. So it's hard to decide what level of physics to go into. So I'm just going to do some stuff. This is not the Foundation series. This is, again, Star Wars. And I know, he said science fiction, and I'd really like to do more science fiction, but this is a great example of orbital motion. This is the Death Star 2 from Return of the Jedi orbiting the moon Endor. And so let's use this as an example to talk about orbital motion. So we need to start with some very fundamental physics. And although Newton didn't explicitly write this way, I like to think of the force and motion relationship with this equation. We call this the momentum principle. This says that the force on an object, what does a force do? What does a vector force do? It changes the momentum, where the momentum is mass times velocity. And you don't have to do this. You could do just force equals mass times acceleration. That works too. There's some advantages to using momentum, but we don't need to get into that. We can just talk about physics. So that's what the momentum principle says. If you want to change the momentum, then you need a force, a net force. The other big idea to consider for orbital motion is the gravitational force. This says that if you have two objects with mass, then there is an attractive force between them. That force, the magnitude of that force depends on both the product of their masses and the distance between their centers, r squared. And then that minus sign just means it's attractive, and the r hat is just a unit vector to make sure that we still have a vector force. I don't like to write things that are wrong, even though sometimes I do. So that's what we have. With those three things put together, we can make orbital motion. And it seems kind of crazy that that's all that it takes, but that's all that it takes. So let's imagine that we have the Death Star orbiting Endor. Here's a picture at two different locations, two different times. So we have position 1 is the Death Star, and it's moving up with some momentum. A little bit later, it's at position 2. It's going the same speed, but it's in a different direction. And why? So that is a change in momentum. Change in direction is a change in momentum. And so what caused that change in momentum? It was the gravitational force with the planet. So, which changes with distance too. So there's some math I'm not going to put in here, but if you do this, you can get a relationship between how fast it's going around in a circular orbit and the size of that orbit. And what we like to write as the angular velocity, or how many times it makes a revolution every second, right? And we call that the angular velocity. And this is the equation for that. So it depends on G, the gravitational constant, the mass of Endor, and the distance between the center of Endor and the center of Death Star cubed. And so we can calculate that. But the important thing is that if I move further away from Endor, it's going to take longer to make an orbit. That's important. That's important for a space elevator. So let's look at a couple of orbits. So these are, this is not Endor, this is the Earth. But on the left here, we have the Earth orbiting. We have 2 satellites orbiting the Earth, and then the Earth is also rotating. So I put a little yellow dot on the Earth so you can see that the Earth is indeed rotating. The blue orbiting object is further away, so it takes longer to orbit. But both of these are not orbiting at the same time the Earth rotates. Now, on the right, if I move my object far enough away, then I can get to the point where the orbital angular velocity of the satellite or Death Star or whatever you want is the same as the rotation rate of the Earth. And this is really important because now I have the object directly over a point on the Earth, always. And we call this a geostationary orbit. And they're very useful because we can put something in space and relative to the Earth, it stays in the same position, even though it's still orbiting the Earth. If you use satellite TV, this is where you put satellite TV satellites in that area. Some weather stations or satellites are up there too, but they're in the same spot all the time, which is really nice. And that's what we have with the Death Star. The Death Star orbiting the planet, the moon, Endor, seems, and you can argue, no, it's not, it's something else. And I accept your argument, but I'm trying to do physics. So if it wants to stay over the shield generator, then it would have to be in a geostationary orbit. And here we have a scene that shows the Death Star and it shows Endor. And we can use this again with video analysis to get some dimensions. How big is the Death Star? How far is it from the surface? What is the radius of curvature of Endor? I can get all of those by doing video analysis. And there is one piece of information that's useful in all of this. And I don't normally like to look stuff up, but this is so common that everyone else uses it. And that's the Death Star number 2 had a diameter of 160 kilometers. And with that, I can get the orbital radius, the distance from the center to center, as 1.5 million meters. And now I can calculate the gravitational force on the Endor based on its rotation rate. And I find that Endor, based on its size, I know its size is smaller than the moon, but if the Death Star is going to orbit in a geostationary orbit that distance, it'd have to have twice the mass of the moon, which, I mean, that's not crazy. It could happen. But here's what's crazy. If you look at this distance, we also know the time it takes for one complete orbit, which would be the same as the time it takes Endor to rotate. We call that a day. So in this case, Endor would have a day that's 34 minutes long. And of course, that's not true, but it's just fun. It's just fun to do that kind of stuff. Okay. So now let's go back to the space elevator, because I mean, it's not a huge plot point. I mean, I guess it kind of is, but sometimes space elevators break or get broken. That's all I'm going to say about the Foundation series. Okay. So here is a space elevator, and we want to do the same thing with the space elevator. We want to have a mass in orbit and we want to have a cable going from that mass down to the surface. And once we have that, we can have a climber, right? We can have a machine that takes its time and it can move up into orbit and then do whatever it wants. So if you had a space elevator on a planet, it would be a great way to get into orbit instead of using a chemical rocket in which you have to carry all your fuel with you and you have to do it really fast before you fall back down. So it's not super easy. A space elevator would make things a lot easier. So imagine that I have that dotted line. That's the distance for a geostationary orbit. And now I move a little bit past that. If I move a little bit past that, then I'm going to need to pull on I'm going to have a force greater than gravity. So I'm going to have an extra force pulling it towards the planet. And I can do that with a cable. And that's what a space elevator is. They're very, very difficult to build because this distance is huge. You need a lot of mass. And it becomes a little bit more complicated too, because once you have all that mass has a gravitational force too. The cable has a gravitational force. So you have to support the cable too. It gets very, very difficult. So we don't have a space elevator. But if I want to model how a space elevator, what happens if it breaks, I have to model the space elevator itself. So imagine that I take this cable and replace the cable with a bunch of masses. So my cable is a bunch of masses connected by springs. I didn't show the springs here. So if you take this middle piece of the space elevator cable, then there's really three forces I need to consider. One is the gravitational force. The gravitational force, it's interacting with the Earth. Two, the cable below it's pulling, right? The mass below it's pulling. It's like a spring. It's like a stretched spring. And then the cable on the other side's pulling too. But what if I want to just break it? The whole thing broke. All the connections between these masses break. It's not in orbit because this piece that you're looking at is moving too slow, right, to be in orbit because it's in the same angular speed as the rotation of the Earth. So it's too slow to be in orbit. So if I break it, it's going to do something that we don't want. So this is a model. I made these models in Python. So this is real physics. It's not a real elevator. But we can take that, it maybe break it into 100 pieces. I'm going to have my cable of 100 pieces of mass, and then I'm going to have my base station at the end, just one mass. And I'm going to have them have the same rotational velocity and then just let go and see what happens. So let's see what happens if that space elevator breaks. So there you can kind of see all the tiny little masses in between. Those are all the pieces that are broken into. So you'll notice that the pieces that are closest to the Earth, they just fall. They're going way too slow. But then at a certain point, they're fast enough to sort of orbit. It's not a circular orbit. And so they'll move away and they'll eventually come back and end up crashing into the Earth too. But the most important thing is that first a third of the cable is just going to hit the Earth. And we already said these are massive things. So a massive thing just hitting the Earth, it just wouldn't be good. Okay. It'd be worth it because the space elevator would be cool. But if it broke, it would be bad. Okay, the next example I want to look at. Again, this one's not Star Wars. So if you're anti-Star Wars, this is one of my favorite TV shows. No, I can't pick favorites. But The Expanse, it started on it ended on Amazon Prime. Super great, based on a book series, but super great science fiction show. I really enjoyed it quite a bit. One of the things in the show is a guy develops a new type of propulsion system that is just like very, very powerful, doesn't use a lot of fuel, and he's just testing it out, and he ends up not being able to stop the rocket. And this is showing the evolution of that. So here's the part that's important. They show these numbers. I'm going to show you those in just a second, that show his fuel, how much fuel he has. It shows the speed, and it shows the acceleration in G's. And so for me, as an educator and someone that loves to do analysis and just take things to where they may want to go, now it's game on. I can get some data from that, and I can play around with the physics. So there's the rocket again. So the questions, well, how fast did that rocket eventually end up going, right? Because it shows you just a little bit. It shows you the progression of the speed and the acceleration and the fuel. That should be enough that I could kind of get a value for the final speed. And, does it reach, a tenth the speed of light, or what would happen? What about the maximum acceleration? Because the acceleration is not constant. And so we can kind of project and say, well, what would the acceleration be? And you could even imagine if, and this is true with real rockets, as you use more fuel, you have less mass in the rocket because you shot it out the back. And so that means that you can you could have a greater acceleration with less fuel. So it could happen. How long does the fuel last? And then how far does it go? These are all great questions that you could try to look at. So let's look at the control panel that we see in the shot and just talk about it for a second, because this is where I got my data. So on the left, you see there is the fuel supply as a percent, then this 5674 MPS. I'm just going to say that's meters per second. It could be miles per second. I don't know. I'm not 100% sure. I just got to pick, right? You got to pick. I'm going to go with meters per second. And then the 3.14 G, I'm going to assume that's acceleration in G's, where 1 G is 9.8 meters per second squared. That's the way we normally do it here on Earth. And this is in the Earth's solar system. So that's where it takes place. And then we have time too. We have elapsed time. So we have a whole bunch of great data there. And I can just go through the video, write down all the numbers with the different times, and I got data. So if I do that, and I did, this is the speed as a function of time. And you'll notice it is very linear. Speed versus time, that means change in speed divided by change in time would be the acceleration, which is the slope. So the slope of this line is the acceleration. And I fit a linear function to this to get the slope. And I get 83.5 meters per second squared at this part of the video. That's what I get for the acceleration. And so that's the change in velocity or the change in time. That's slope of velocity versus time is the acceleration. And we also had that 3.14, it changed to 3.15, 3.15 Gs. If I say 1 G is 9.8 meters per second squared, then I just multiply those two together and I get 30.87 meters per second squared. So you see there's a problem, right? Because looking at the change in speed, 83 meters per second squared. Looking at the G meter, 30. So they're not the same. And normal people would say that's fine. But I want to say it's not fine because I want to find out what's going on. And then so the first idea was maybe that capital M is not a lowercase m. Maybe it's not meters. I like to use meters, but some people use feet. You could be some other unit. So you can just do that same thing. You can do unit conversion and say, well, then what is one? If those two units are the same G's and the M unit, whatever it is, then that 1 M would have to be 0.37 meters. So, or maybe this guy lived on Mars. Maybe it was a Martian G, but that would actually make it worse because the gravitational field on Mars is even less. So there's some inconsistencies here. So we can go back to those original questions that I posed, but we're stuck, right? Because the acceleration also goes from 4.28 Gs at 2 minutes. So it increases. And that's actually, if you look at the data, it's inconsistent with the change in speed. If you go, you can look at that elapsed time, and that's not the speed that it would correspond with that acceleration. So, and in fact, the linear acceleration based on the change in speed was 617 meters per second squared. So if you from the very beginning of the clip to the very end of the clip, looking at the elapsed time and the change in speed, I calculated the acceleration and I got 4,700 Gs, and that's not good. That's not good because you can't survive that. And I mean, that's not even close to being survivable. That's a bad number. That's a bad number. But here's the best part. Here's the part that I want to talk about, because I have worked with TV shows. I've worked with MacGyver, and MacGyver's my, it's fake. It's science fiction. And so I would come up with some explanation or some calculation or some values. And sometimes you could get the producer saying, but that's good. I like your, someone probably calculated that readout and put down the numbers. And then the producer said, I like your work, but I want it to be bigger. I want more speed. I want it to be more speed. And then the science consultant would say, well, that's not really the way it works. And then they said, well, that's fine. Just change it. And so they did. And so I'll just put a new number. And that's fine because, it's trying to tell a story. Remember, we're trying to tell a story. And that's how that happens. It's still fun. Okay, next, I'm going back to Star Wars. I can't help it because there's some stuff here I like a lot. So this is from The Mandalorian season 1. And he is doing stuff. I don't want to give away the plot, even though we're already on finished season 3. But one of the things is he's trying to find out some people inside of a building. So he takes his special Mandalorian rifle and he uses the scope, and he can see through the walls, and he sees these people there. So let's talk about whether this is realistic or not, and how it actually work. So there are really 3 ways that we can see things. Number 1 is reflection. And I took this picture. I like to use as many pictures of stuff that I took as possible. You can see the moon here, which is still mind-blowing that you can take a picture of the moon with your phone, but I took this with my phone. And we can see the moon because sunlight shines on the moon, reflects off the moon and into the camera or into our eye. But we see things because light reflects off of them. I can see the trees in this picture, because I'm not sure where the light's coming from, but there is a light and it reflects off those trees and into the camera, and I can see it. So everything around you that's not a light, you can see because there's light. And if you turn off all the lights, you can't see anything, right? There's no light to reflect off stuff. You can't see the stuff. And if you've been in a completely dark room, you would know that's the case, and it is really dark. The next way that we can see things is kind of one that you don't always think about, and that's with shadows. So if you break a leg or a bone, don't do that. But if you do, you'll go get an x-ray. And so the way the x-ray machine works is it shoots out x-rays, which are just light. It's just light with a shorter wavelength. That's all it is. And that light passes through you, and then it hits a detector. And so the detector shows shadows of x-rays. And so this is what happens if you look at the x-ray of a bone. This is a broken ankle. Unfortunately, this was one of my kids all did sports, and so this was one of them. So, but if you're going to break your leg, I'm going to at least use it in my talk, right? So they're better now, so don't worry about that. Here's another shadow picture. This is me and some of my friends looking at the solar eclipse. And so the solar eclipse is very awesome, but also not very bright. And so the main thing that you're seeing is the stuff behind us, and we just block out some of the light, and that's how you see it. So it's a shadow view. The third way to see things is with emission. So sometimes we can get things that produce their own light. So you're probably looking at a computer screen or TV, and that TV is producing light. So even if all the lights were out, you'd still be able to see it. So the light's coming straight to you. This light bulb produces light, the light goes straight to you. And this has to do with the Mandalorian. I told you that. So here is my favorite example. Here is the broiler element in an oven. If you turn that on, it gets hot. And eventually it gets so hot that it glows and you can see it. So we have this transition between things that are hot that you can't see into things that are hot and they do give off light that you can see. And in fact, everything gives off light. Everything gives off light that depends on its temperature. And we call this black body radiation. So the hotter things get, the more shorter wavelength light they give off. So a normal object at cold temperatures would give off longer wavelength light that you can't see, but it's still giving off light. But you can see it. You can see it. This is a picture of the oven element. Before it was glowing, it wasn't giving off visible light, but it is giving off light, and you can see that light with an infrared camera. And so I took this picture with an infrared camera, and I'm obsessed with infrared cameras. So I'm going to show you two of my favorite infrared cameras. These are two infrared cameras. The one on the left is the FLIR 1. It's a camera that just attaches to your phone, which is pretty cool because, 10 years ago, the cheapest camera would be way too expensive to even think about affording. And these are very affordable, and they're not cheap, but they're not there's something that you could get, and you can get great pictures with them. Now on the right, that's a very high-end FLIR camera that I borrowed from FLIR, and I had a lot of fun with it, but it's scary how expensive it was. So you can get all sorts of infrared cameras. Now, when we take an infrared picture, this is an infrared picture of my power supply for my computer plugged in. But the important thing is that if we can't see these wavelengths of light, how do we translate them into stuff that we can see? The best way is with this false color idea. And so in this color palette, the darker purpler colors are colder, and then the brighter yellow, whiter colors are hotter. And then we can adjust that scale, the color scale, to match whatever temperatures we want to look at. So in this particular case, I switched it to Fahrenheit. This goes from 70 Fahrenheit for the coldest stuff up to 89.7 to the hottest stuff. So if it gets hotter than that, it doesn't change color. If it gets colder than 70, it doesn't get any darker. So just so you can see how these things work, if you play with one of these cameras, the best thing is that it turns out the things that you can see are just kind of cool. You don't realize how, if you have a cable for a power cable, the cable gets hot. You can tell which cables are running electricity through them and which ones aren't by their temperature. You can see reflections in the table here, even though it's not a mirror, because infrared acts differently than visible light. So here is a picture I took. These are two pictures that are the same thing. On the left is an infrared picture. On the right is with the visible camera. And so here is I took this a while ago. This is one of my kids on the other side of a glass window. And you can see the visible light goes through glass. If you look at that same picture with the infrared, you cannot see through the glass. Infrared does not go through glass. Okay, so I would just be, whatever you're seeing in there is just a reflection of things on the other side of the window. So you can't do that. But here's the opposite version. Here's again, two pictures, visible light on the right, infrared on the left, holding up a plastic trash bag. And I love this demo because you can see through the trash bag. So infrared goes through the trash bag, but visible light doesn't. So different wavelengths of light interact differently with matter. That's just the way infrared and all light works. Radio waves go through the walls and visible light doesn't. So it's not that big of a deal. So can you see through the walls? Could the Mandalorian use this thing to see through the walls with infrared cameras? And this shows up in movies a lot. They say, oh, we're going to use infrared and we'll look through the walls. No, you can't. You really can't. Well, you can if they're made of plastic trash bags or some other special materials, or if they're super, super, super thin. Or there is one other way. If you have like a person and the walls are really thin and the person is like heating up the wall, the person is close enough to the wall and the wall is thin enough, then the person could heat up that wall and then you would see the change in temperature of the wall. You can actually use this with the infrared camera to find water pipes. So if you turn on the hot water in the bathroom, that part of the wall will get a little bit hotter and you can see it with the camera, which is kind of cool. It works better in the winter, and I had a picture, but I couldn't find it, and it's not cold enough here right now. And then you can do the same thing with cold water if the walls are hot. But if you get the difference in temperature, you can actually see where those things are. Okay, back to another Star Wars. This is one of my favorite. Just a reminder, Star Wars Day is May 4th, right? I hope you know that. May the 4th be with you. It's something that I always try to create some Star Wars content, science content on May the 4th. So I've been doing it for 10 years. This is the first scene of Star Wars Episode 4. It wasn't called Episode 4 at the time. And this is the first time we see a space battle, the first time we see a blaster bolt. That's the first blaster bolt you see in Star Wars ever. And they're not lasers. I mean, we could talk about them not being lasers, but they're not lasers for a lot of different reasons. One, you can see them, right? You can't see lasers, especially in space. And they're obviously going too slow. But how fast are they going? So I want to this is something I did for Star Wars Day a while ago. And I said, I'm gonna analyze all the blasters in Star Wars, all the times we see blasters, and I'm gonna find out how fast they're going. And I did episode 4, 5, and 6. That's what I did. So again, I'm going to use video analysis. In video analysis, there's a couple things I need. I need the size of stuff. I need to know how big things are. So in this case, I again cheated. This is the Rebel Blockade Runner. I looked up the length. I don't like looking up stuff, but I looked up the length. The other thing I need is a time scale, right? If I look from one frame to the next, I have the frame rate of the movie. And if that movie is playing in real time, then the time difference between frames is the time difference in real life. And so that's good. And I don't think this is in slow motion. Well, it's not supposed to be. So I can use the frame rate as the real time. And I only see this blaster for 3 frames, but I can still get an estimate of its position in each frame and get a velocity. So here is the data from Tracker Video Analysis. That's the program I like to use. And you see the 3 points, that's position versus time. It looks like it's enough to get a line. It's not a great line, but it's a line. So if I fit a line to that, I can get the slope. The slope of that line is the speed, and that gives me the speed, which is this A term right here. This use video analysis estimate. I've got all that. And then I can actually also get an estimate for the uncertainty in the velocity, which I should do if I only have 3 data points. I can't just say that's the velocity. I need to get an estimate of uncertainty. So here I have a value of this first shot of 1.8 times 10 to the 5th meters per second, plus or minus 6,000 meters per second. So that's a pretty big range, but it still tells me something. The next shot, well, there's a couple space shots. I did all the space shots. After that, we see some handheld blasters. And so this is the first handheld blaster you see. You can't really see in the clip here, but there's a stormtrooper right there on the left, firing to the right. There's a lot of smoke because, special effects and stuff. So I can again do the same thing. I can say, well, what's my scale? In this case, it's a stormtrooper. So I can, say they're like a normal human. I can estimate the size there. And then I can mark the position of the blaster in each frame and get the following data. And I get the speed here. And you'll notice that's quite a bit slower. 15 plus or minus 2 meters per second. Okay. Now I'm going to go through the whole original trilogy, which took me a long time, but I did it. And this is what I get for the distribution of speeds. And I called these ground-based blaster speeds. So these are anything with where you can see a person. People size stuff. So it could be a couple of spaceships like the speeders on Endor. I think I included those in here. But any time that would be a person-sized blaster. And so the histogram shows that most of those blaster shots were in the lower speeds, around 25 meters per second, somewhere around there. There were some that were much faster, even over 200 meters per second. But for the most part, most of them were quite slow. If you do the average, it's the average of all the data, 34.9 meters per second. Now here's something interesting, and I was going to add a picture in here, but I didn't. And you should, for your physics project, find out how fast a Nerf dart is. I did it. And there's different Nerf darts, but I got 10 meters per second for a Nerf dart. So if you take your Nerf gun and you shoot that dart, that's about 10 meters per second. So that's kind of cool. I mean, we didn't have a lot of Nerf stuff when I was growing up, but if I did, I would have definitely pretended like it was a Star Wars blaster. And I wouldn't have been wrong, right? So, okay, so let's look at all the space shots too. So if I make a histogram with all the ground-based shots and with all the space-based shots, which would be, X-Wing shooting TIE fighters shooting the Millennium Falcon, all that stuff. I have to plot it on a log plot. And I didn't do this the best way. I did a long time ago, but I just took the log of the blaster speed instead of doing a log plot because of the program I was using. And so you see the green data is the blaster, ground-based blaster. The blue purple stuff is the space-based. And this is the log of the speed. So these purple things are way faster, but they sometimes overlap. And then there's some that are way, way, way faster. And then at the very end, I have 2 other data points that are super, 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 super fast. And if you know what those are, it's from the Death Star. That's the Death Star blast in Star Wars Episode 4 and in Return of the Jedi. And so they were way faster. I did include those in the data. Now, what if you did this? What if I said, okay, how about I go the other way? What if I just plot the angular velocity of the blasters? What if I ignore all data about the size of stormtroopers or the size of the rebel blockade runner, and I just say 1? The width of the frame is 1 unit, whatever that may be, and then I'm gonna get the speed that way. So this would be essentially radians per second. That's the angular size, that speed that it moves across the screen. And you get this. So now you get no difference at all. You get no difference between the space-based lasers and the ground blasters, and the ground-based blasters. And it tells you something really interesting. It tells you that, of course, blasters aren't real and they're not really shooting anything. We already knew that. But more importantly, they're drawing these blasters on each frame, and it didn't matter whether there is space or not. Every blaster takes about 3 frames to get across the picture, no matter what it is. So that way we can see it, right? So again, it goes back to that. If I made the blasters as fast on the ground as they are in space, then you couldn't see them. It wouldn't even take a frame to get past 10 meters. It'd just be nothing, and that wouldn't look cool. You wouldn't even know you're shooting. And they want to show this visual effect, so they have to do it in the angular size. And I don't even know if they were thinking about that, but definitely they're drawing. 1, 2, 3, three frames. There, done. 1, 2, 3 frames. And the Death Star is a little bit different. Now, so I did this experiment. It took me a long time. I wrote it up for Star Wars Day. I had a great time. And then I was not the science consultant, the technical consultant for Mythbusters the whole time. Probably the last 5 seasons of the regular Mythbusters, but they did use this data on one of their great shows, which they had 2 Star Wars episodes. One of the Star Wars episodes was, they said, can we dodge a blaster? Could he really dodge a blaster bolt? And so they wanted to know how fast it was. And they said, hey, you already did this data. I said, yes, I did that. So they used my data to reproduce a blaster bolt. And they used a tennis ball shooter thing. That was their blaster. And it's funny because they used a velocity of 58 meters per second. So I remember having the discussion. I said, the average is 34. And they said, well, we think 34 might be too slow and it might be too easy to dodge. And then that's no fun, right? You don't want to have a myth. And I worked on myths later that they were too hard to show or too easy to disprove. And that's no fun. It's got to be on that knife's edge of, well, it's kind of plausible. And I think that we could get to the point where, we're not really sure. And this is one of those cases. So they said, well, what if we use something faster? What if we use 130 miles per hour, they said. I said, there are blasters that are 130 miles per hour. They're 58 meters per second. There are some like that. So it's not wrong. It's just not the average. And so that's what they did in this case. And so they if you didn't see the episode, you should. It's really a great one, especially because they Mythbusters, they love to build stuff, and they built these Star Wars sets and stuff like that. It was great. But then what they would do is to take their fake blasters and shoot them at Adam or Jamie and see if they could dodge them. And this is him not dodging in slow motion. I just thought it was great. It was a great shot. So it's a little tennis ball with the thing on the end to kind of make it go straight. So that was what they did, and that was that. So I'm gonna stop there, and there's a whole bunch more science stuff that we could talk about. Again, if you want look at a whole bunch of more. Everything I talked about in here is on that list of science fiction and Star Wars stuff that I posted, and you can go look at more data. But thank you very much for your time. I'll be happy to answer questions. And thank you.
Bob, can you turn the lights on, please? Oh, any questions, please, for Dr. Lane? I'm sorry?
I have one.
Yes.
So, in the Mandalorian, seeing through walls, section of the talk, have you thought about the technology that they can pick up sounds like through windows and things like that, and maybe it's like a sonar type of a vision.
Right. Yeah. So there are some really currently some great technologies to see through walls. There is MIT developed some. Essentially, it's Wi-Fi. It uses Wi-Fi to like look through walls and see where people are there, because you don't get as good of a signal through there. Sound could possibly be one option, and that's the fun part. It's not, is this right or is this wrong? It's what cool science can we talk about, and what other ways could we make it work? Sound, I think, is definitely an alternative. I mean, the thing I'm just trying to show you that it's not infrared. And they do that in a lot of shows. They like to say, oh, we'd see through it with infrared.
On the space elevator references, I think that there are some folks who are working seriously on looking at that. I don't know if that's true or that was a spoof. That someone was doing that. But did your work show that this simply isn't possible?
So, I mean, there's been a lot of papers published on space elevators. It's kind of awesome. And I didn't show space elevators do or do not work. The main thing right now is it's all about material science. Can we get material that would be strong enough to support a space elevator? I just want to say, what would happen if it broke? You know, really, like, again, number one, I can use this to talk about what is a space elevator, what's a geostationary orbit. That's what I like to do. And then number two, bring it to the extreme. What could we model how it would break? But space elevators are a legitimate research topic, and people do that all the time. And there's a lot of research on space elevators.
Dr. Allain, may I ask you a question about Star Trek?
Yes.
I sometimes give talks about the original series, and sure enough, someone will always ask the question to me, do you think we'll ever have teleportation? And I look at them, and I'm not a physicist, but I look at them and I say, if you really think about it, the way they do it in Star Trek, it's really death and cloning. And you're dematerialized on the spaceship, and all that does is record every atom in your body, and a beam is sent with the information, and somehow there's an energy to matter reassembler wherever they're getting transported to, and it's just read off and a copy is made. Am I somewhat right in that?
Yeah, I mean, of course, it's not real. And, you know, the teleporter is so cool because we're talking 1960s. And I don't know, I think it had to do with, like, how can we get these people down to a planet and not have to use a model shuttle every single time? And I'm sure someone said, what if we just make up this thing that just puts them there magically? And they said, do that. You know, I suspect, I don't know for sure, I suspect it was a production issue, not
It was.
But then what happened after that? How many times in the giant universe of Star Trek, and there's so much Star Trek stuff out there, how many times does a transporter play a plot point, you know, where someone gets cloned accidentally, someone gets lost in the transporter beam, you know, all these things are, or even in Picard season 3, the transporter was a big deal. So I love that. It started with just like, I don't want to say how these people get down to the surface. It's transporter, and it becomes a big plot point. So, but I agree that you, when what you're saying is they're destroying the person and then rebuilding them. That's why Dr. McCoy hated transporters.
Engineers, they love to change things. And
Yeah.
by the way, the research I did, and you're absolutely right, they didn't finish building the shuttlecraft by the time the series started. And so they had to come up with something else. You're exactly right. Thank you very much.
Thank you.
Sorry for noise. We have a question. Did you get your question?
No, I did not. On the expanse, on the Epstein drive, did you come up with the velocity in your research? Did you come up with, from what your data, based on the series, what indicated the velocity would be?
Yeah, I didn't. Because what happened was I started looking at the data from the acceleration and everything was inconsistent. So I said, I analyzed it somewhat, and you could get a bunch of different answers because the data, the acceleration didn't match the velocity anyway. So I left it as a homework assignment for the reader.
Were you on site for most of the Mythbusters
No,
filming?
I was never on site.
Okay.
Then I got into Mythbusters because I was a huge Mythbusters fan. And when I started writing about science and stuff, I would like to use Mythbusters as examples. At some point, they changed production companies and they wanted to include more science panels in the show. And what made Mythbusters so great was that Adam and Jamie, they were just, great builders. They're not scientists. They're just great builders. And that's what made it fun. And it didn't matter what they said, because they're not in an expert voice. But as soon as they start putting in there, I'm going to explain Newton's third law, then you don't have to be 100% correct, but you can't be wrong. And they were just doing wrong stuff. So I would write about the wrong stuff. And they said, okay, well, fine, then you're going to be the technical consultant. And at first it was really just, hey, here's a clip of Adam. Is that okay what he said? And if it's not, we can't change it. It doesn't matter. And so I'm like, well, it's Adam. It doesn't matter what Adam says, right? Because he's Adam. It matters about the science panels. The last season of Mythbusters, I was heavily involved in script writing and setup and finding things and doing calculations. I did all that stuff for the new Mythbusters and Mythbusters Juniors too, but it was all remote.
I see.
Sadly.
Thank you.
I have a question about acceleration and the limits that a body can take. You said that it was impossible to, what was it, 4,000 Gs or something like that? I can buy that. But what is the maximum? And what would the maximum be if you were living in an incompressible fluid?
Yeah. So there used to be a NASA table of maximum G forces that you could take, and it depended on the orientation too. So they had like eyeballs in, which is mean my head's accelerating that way and my eyeballs are getting pushed in, eyeballs out, eyeballs. So I don't know why they did it in terms of eyeballs. But for a very short amount of times, it's somewhere around 20 Gs dependent. It is time dependent. And I don't know anything about the underwater fluid thing. It seems to make sense. That's used in science fiction a lot. I don't really know a lot about human bodies except that I have one.
I had to read a story about, actually it's a science article, and they actually had animals that were living, basically if you have enough pressure, you can dissolve oxygen in the water to the extent where it can be breathed. It's just, it takes a lot of effort to breathe water that's under that much pressure. Or it's actually very hard to breathe water because it's a lot of mass going in and out. But if you're under like 5 atmospheres, you can actually dissolve enough oxygen in the water to breathe it and live for a while.
Isn't that what they used in the abyss? When
Yeah,
the
they
guy
did.
Yeah.
Yes.
Yeah, okay.
Anyway, the thing is that they did experiments in centrifuges. Of course, they didn't do them with people; they did them with rats. But they had an enormous—I can't remember what it was, and I was hoping you would be able to tell us. But they had an enormous number of G-forces. It was basically they had a pregnant rat in there, and the mother died, but the fetuses in her womb were alive, and they were doing something like 1,000 RPMs or something like it was a tremendous amount of G-forces. So there is some basis to that, but that was when I was a kid, so I was hoping that they would have sophisticated that a little bit more.
Yeah, I've seen stuff like that too, but I don't know anything further about any of those research studies. But yeah, the idea of putting things in fluid seems to, at the very least, it's a good plot point. I mean, it's a good mechanism to get, to get your plot moving forward.
Are there any other questions this evening?
I got one here.
Yes, please.
Just real quick, what of all the sci-fi movies you've seen or consulted on, what movie or movies do you think get it right? Get it the most right, and on the flip side, which ones are the most egregious when it comes to physics as we understand it?
I'll start with the most egregious. It's Star Wars, right? But that's what makes it so great, because they don't care. If they don't try to explain things, it's fine. Who cares? Until they want to explain the Force with midichlorians. But the spaceship battles are so bad in terms of physics, but I love them so much, and I wouldn't want to change it. Then there are great space battles. The Expanse is really good, and in fact, the showrunner has a BS in physics. So I did talk to him, and I enjoyed that very much. Interstellar was, also had a really great science consultant. Interstellar, the whole black hole thing, they found out new stuff by modeling black holes, and I thought that was pretty awesome. So the Expanse and Interstellar, I'm going to put near the top just because I like them so much, and I think they did a great job. And then I'm going to put Star Wars at the bottom, although there surely are some really bad ones. I'm thinking, what was that one asteroid one? Was it not Armageddon? The one before that. Well, it was really bad. They were really bad. They were so good movies. I really enjoyed them though. So.
And with your
Yes.
with your intense. Oh, go ahead. Oh, I'm hearing myself echo. With your intense evaluation of the science, are you still able to sit back and relax and enjoy a good sci-fi movie?
Absolutely.
Oh,
I mean, the one I'm thinking in my mind, though, there's one scene. I love the movie though. Okay. And it could be science fiction if you want. It was the Amazing Spider-Man with Andrew Garfield, the second one where he's trying to beat Electro, and there was a scene where he talks about, oh well, magnets would make this work, and it's just stupid for no reason. It doesn't even make sense. You could come up with a billion things better than that, and it wasn't even important. But I still like the movie. So when I'm watching a movie, I don't think I have ever cringed about stuff, because I love that stuff so much. I love superheroes. I grew up with comic books and science fiction, reading science fiction books, and we didn't have the stuff that we have today in terms of the great movies and shows. We had Star Trek, Star Wars, 2001: A Space Odyssey. That one's pretty good. And we had a couple superhero movies. That was it. So
yeah, I know.
Are there any other questions from our visitors here this evening? I see none. I think they want to go back to the campgrounds. Anybody on Zoom before we close the session for the evening?
Dr. Allain, thank you.
Thank you for having me. I had a great time.
Thank you so much. Lots of fun.
Really crazy stuff. And I'm going to go back and watch movies. All right, thank you very much. Have a great